Today we're going to start chapter 16, which is on acid-base equilibria. And this is a nice kind of continuation, and we're going to bring back equilibrium problems like what we saw with the last chapter. But as I said before, there's a little bit of a shortcut that we can possibly do that I'll show you in a later on video. Okay, so acids and base. There's a couple different ways that we can identify and define what an acid and base is. Okay, so one way is we can use the Arrhenius definitions. So Arrhenius acid, it's a substance that increases the hydrogen ion concentration when dissolved in water. So if we have something in brackets, that's saying concentration of hydrogen ion. Arrhenius base is a substance that increases the hydroxide ion concentration when dissolved in water. Now this is helpful and everything, but in the 1800s we had two scientists, one Danish and one English, that worked independently, and they found another way of how we could define what an acid and base is within a reaction. We had Johann Bronsted and John Lowry. So they came up with, even though they worked independently, they came up with the same conclusions. And so we have another definition of Bronsted-Lowry acid. Bronsted-Lowry acid is a substance that donates a proton, and the way that we represent proton is a hydrogen ion, because you think of a hydrogen atom, it has one proton, one electron. And if we take away the electron, so we have an ion, we're only left with that proton. So we can find that proton as a hydrogen ion. A Bronsted-Lowry base is a substance that accepts a proton. Okay, so let's kind of look at an example of this. So our first reaction, we have hydrochloric acid reacting with ammonia to give us a chloride ion and ammonium ion. So if we look and see what happens to figure out which one's the acid, which one's the base. So HCl, we have HCl over on the left-hand side. Then on the right-hand side, we have a chloride ion. So that's telling me that the HCl donated a proton. So HCl is our acid. Now NH3 goes to NH4 with a +1 charge. So it accepted a proton. That's telling me that NH3 is a base. Okay. Now with these types of problems, we're always going to have an acid and base on the left-hand side. On the right-hand side, we also have an acid and base, but they are the conjugates. Now a conjugate acid is a product that is the counterpart to a reactant that is a base, and a conjugate base is a product that is the counterpart to a reactant that is an acid. So up here, HCl was our acid. That's telling me that the chloride ion is going to be the conjugate base. Ammonia, NH3, was the base over on the left-hand side, so ammonium is going to be the conjugate acid. So the conjugates are the exact opposites of what they were on the left-hand side. Let's kind of look at another example. So we have nitrous acid reacting with water to give us nitrite ion and the hydronium. So HNO2 goes to nitrite, so it is the acid. Water goes from H2O to H3O plus, and this is called the hydronium ion. I have that on the other side of the notes. So this is going to be our base. Now the nitrite ion, that is our conjugate base. And the hydronium ion is going to be our conjugate acid. Now let's look at this one. We have ammonia reacting with water to give us ammonium ion and hydroxide. So the ammonia goes to NH4 plus ammonium. This is our base. Water goes from H2O to hydroxide, so it is our acid. Since the ammonia was the base, the ammonium is our conjugate acid, and the water was our acid, so the hydroxide is our conjugate base. Now let's look at one more thing. Let's look at this reaction. Water reacting with water gives us hydronium and hydroxide. Well, one way that we can look at this is we can say that we have the acid, then the base, C acid, C base, or we can have base acid. Then of course the hydronium has to be the conjugate acid and the hydroxide has to be the conjugate base. Since we have the same two reactants, water reacting with water, it doesn't matter which one is going to be the acid, which one is going to be the base. On the right hand side, the hydronium definitely has to be the conjugate acid. The hydroxide has to be the conjugate base, excuse me. This reaction is called autoionization because we are ionizing water. Now, since our reaction is in equilibrium, if we wanted to find the equilibrium constant, products over reactants, and if we look, our reactants are both in liquid form, so we can't use them. Our products are both aqueous, so equilibrium constant, K of C, is equal to concentration of the hydronium ion times concentration of the hydroxide ion. Now, since this is specific for water, we can say that is the K of W. So the K of W, or the water constant, is equal to the hydronium ion concentration times the hydroxide ion concentration. Now this constant, same number all the time. It's going to be 1.0 times 10 to the negative 14th. With acids and bases, a lot of times we talk about what is the pH. Okay, so what is the pH? Well, the way that we find it is we take the negative log of the hydrogen ion concentration. And we do this due to the hydrogen ion concentration in aqueous solution being very small. It gives us a number that we can kind of work with and visualize than dealing with very, very small numbers. Now, the pH is a scale. It ranges from 0 to 14. From 0 right up until 7, not going along with 7, so we can be at 6.9999999 and still not be right at 7. Solutions are going to be acidic. Right at 7, and 7 only, 7.0, it's considered to be neutral. Anything higher than 7, so that we can be 7.1 all the way up to 14, and it's going to be basic. Now, going in the opposite direction, if we have the pH and we want to find the hydrogen ion concentration, we take the antilog of the negative pH. Because if you look at a calculator, get it right on here, okay, here's our log button, then right above it is 10 to the x. So that's why it's called the antilog, because it's the opposite. And with the calculators, what they try to do with a lot of the functions is they would put the reverse or the anti right above that function. Now, along with pH, we also have pOH. And the way that we find the pOH is the negative log of the hydroxide ion concentration. And once again, we do this due to the hydroxide ion concentration in an aqueous solution being very small. The pOH scale, 0 to 14, just like the pH scale, but it's in reverse. So from 0 up into not including 7, solutions considered to be basic. At 7, neutral. Anything higher than 7 up to 14 is acidic. And the way that we can find the hydroxide concentration is we take the antilog of the negative pOH. Since the pH and the pOH have the same scale from 0 to 14, if we take the pH and we add the pOH, it will give us 14. So let's kind of look at two examples. Let me zoom out. Okay, so our first example says, what is the pH of a 5.60 times 10 to the negative 6 molar sodium hydroxide solution? Now, subsequent videos later on this week, we're going to do a couple more examples of this and some other problems. So if you're looking at the assignment and you can't figure it out, just wait. A video will be coming out soon. So with this one, since we're given concentration of a base, how do I know it's a base? Because it has hydroxide in it. So sodium hydroxide, if we break that apart, we get sodium ion and a hydroxide ion. And if we look at the reaction and try to balance it, we notice that everything's on a 1-to-1 ratio. So whatever the concentration of sodium hydroxide is going to be also equal to the hydroxide ion concentration. So that will give us 5.60 times 10 to the negative 6 molar. Now, with these problems, this is kind of nice because there's more than one route that we can possibly take to get to the final answer. And I'm going to show you the two routes with these two examples I'm going to do for you today. Now, since we do have the hydroxide concentration, one route is we can find the hydrogen ion concentration from the hydroxide. So if we go back to our formula, K of W, water constant, is equal to hydronium ion concentration, or in some cases this is also just the hydrogen ion concentration times the hydroxide ion concentration. So the K of W, when we found out that that's 1.0 times 10 to the negative 14th is equal to, we'll just use the hydrogen ion concentration because it's a little bit easier to write, times our hydroxide, 5.60 times 10 to the negative 6 molar. So we need to get the hydrogen ion concentration by itself. So we're going to divide both sides by 5.60 times 10 to the negative 6. Times 10 to the negative 14th divided by 5.60 times 10 to the negative 6, and I'm coming up with 1.79 times 10 to the 9th molar for my hydrogen ion concentration. Excuse me. Okay, now that we have our hydrogen ion concentration, we can find the pH. If you kind of looked back at the first part of the notes, pH is equal to negative log of the hydrogen ion concentration. So pH is equal to negative log of the 1.79 times 10 to the negative 9th molar. So we're going to put that into our calculator. Negative log 1.79 times 10 to the negative 9th. And our answer comes out to be 8.75. Okay, so that is one route that we can possibly take. Next, the other route that we can take, we're going to kind of go back here since we said, the sodium hydroxide concentration is also equal to the hydroxide concentration. We're going to start from there. We can find our pOH first. So pOH is equal to negative log of the hydroxide ion concentration. Negative log 5.60 times 10 to the negative 6 molar. Negative log 5.60 times 10 to the negative 6. And come up with 5.25. Now that we have our pOH, we can find the pH by taking 14 minus pOH. 14 minus 5.25. And we come up with 8.75. And that's what we came up with earlier. And it doesn't matter which route we take because we come up with the same answer. So let's look at our second example. Okay, what is the hydroxide ion concentration of a solution with pH of 8.12? Okay, so once again, with this one, we have two possible directions or routes that we can possibly take to find the answer. So one route, since we already have the pH 8.12, we can find the pOH. Alright, so to find the pOH, we take 14 minus pH, 14 minus 8.12. And we should come up with 5.88. Now that we have our pOH, we can find the hydroxide concentration by taking the antilog of negative pOH. Concentration of hydroxide, 10 to the negative 5.88. Negative 5.88. And I'm coming up with 1.32 times 10 to the negative 6 molar. Okay, so that's one route. Now the other route is, since we do have our pH, we can find the hydrogen ion concentration first by taking the antilog of negative pH. So 10 to the negative 8.12. I'm coming up with 7.59 times 10 to the negative 9th molar. And I gotta change out the battery, so hold on real quickly.